Okay, so what we're going to do is look at using calculus to analyze another curve. This one's a little bit different because it's not a polynomial. We're going to look at the natural log of x squared plus 1. And again, off to the right is the graph, so we can see that this graph has certain properties. But again, we need the calculus to kind of verify what's going on and to pinpoint where these points are. Now, just by inspection, it looks as though we have a minimum point here at 0, 0. Which again we can verify. The inflection points, though, are a little bit hard to see. Remember that an inflection point is where the graph changes between concave down and concave up. If I had to guess, it would be somewhere around here and here. And again, we're going to use the calculus to kind of figure out where that is. So the first thing we need to do, and there's a variety of ways you could organize this information, but just remember, your first derivative has where your increasing and decreasing information is. And we can further use that to figure out where the minimums and maximums of the graph are. The second derivative gives you all the information about concavity. So, we could either just take the derivatives and then use the information, or take the derivative and then get all the information out of it. I like to do, take a derivative, take all the derivatives and then and then find all the information. So what I'm going to do up here is just you find all the derivatives. So f prime of x. Now, since it's a natural log of something, we know the derivative is 1 over the something times the derivative of the something. So we have that there. And if we simplify that, because that's going to be important if we have to take another derivative, that's 2x over x squared plus 1. So I'm just going to put that in a little box here. Well, maybe not a box, but okay, I'm just going to let it there. Then if I want to go on to the second derivative, well, to find the second derivative, I need the quotient rule on the first derivative. So that requires that we know the derivative of the numerator and the denominator. So that means that this is going to be, well, let's see. So we have 2 times x squared plus 1, the derivative of the top times the bottom, minus the top, 2x, times the derivative of the bottom, which is 2x. And that is all over x squared plus 1 squared. Now, yes, we do need to simplify that because, again, we're going to be doing something with the second derivative, so that means we're going to have a simpler expression. So we have 2x squared plus 2 minus 4x squared, and that again is all over x squared plus 1 squared. And combining like terms, we have 2 minus 2x squared all over x squared plus 1 squared. So that is our second derivative. So let's get all of our information from f prime of x first. So the f prime of x, again, is 2x over x squared plus 1. And we want to know where that equals 0 because that's where our critical numbers are. Now, ordinarily, we would also look where the denominator is equal to 0. We actually have a denominator in this problem. But since x squared plus 1 is never 0, you're never going to be able to square a real number and add 1 and get 0. So we can just ignore the denominator. Or, once we know that the denominator is never 0, we could multiply both sides by the denominator. And multiplying the right-hand side by anything is just going to give us 0 anyway. We get 2x equals 0 or x equals 0. So that is definitely a critical number, okay? So what we can do from there is test to see what's happening on either side, and we're just going to go full blast on this problem. We're going to find everything that we possibly can. So I'm going to make a sine graph for f prime just to see what's going on around 0. So if something's happening at 0, I'm going to try -1 and 1. And if I substitute -1 into the first derivative, again, remember that tells me that if I get a negative number, I know that I'm decreasing at that number. And if I get a positive number, I know that I'm increasing at that number. So we plug in 2 times -1 over -1 squared plus 1. 2 times -1 is -2. -1 squared is 1, and 1 is 2. So we get -1, and again, the value doesn't really tell us the story as much as the sign does. We know that at -1, and on that entire portion of the interval, it's decreasing. Okay, so there's -1, and if we do something similar for 1, Simplifying each, we get 2 over 2, which is 1, which means we're increasing at 1. So again, drawing my little direction arrow there, we know it's increasing. So right there we can say increasing on 0 to infinity, decreasing on negative infinity to 0. Okay, and again, if we look back up at the graph, it tells the same story. It is sinking before 0 and rising after 0, so that's not a big surprise. We also know that there is a relative minimum at x equals 0. And again, looking at our graph, that tells us a story, and looking at our derivative sine graph, that tells a story too, because we go from decreasing before to increasing after, so there must be a minimum at x equals 0. We'll find the final point later on when we summarize everything. So now let's move on to the second derivative. Now the second derivative was, if I recall, 2 minus 2x squared over x squared plus 1 squared. And again, we want to figure out where all the action is happening, so we set it equal to 0. Again, we know the denominator is never 0, so we don't consider it. Now, again, another perspective of looking at when a fraction is equal to 0, we know that 0 over something is 0, as long as that something is not 0. And we know that something over 0 is undefined. So the shortcut for setting a fraction equal to 0 is just looking at where the numerator is equal to 0. Now I can move the 2x squared to the other side and divide by 2, and that tells you that. Now remember, there are two solutions to something like this, right? Plus or minus 1. There's no word problem associated with this, so we don't have to exclude negatives here. So we have two possible points of inflection. So just remember that these are only possible until you do analysis. So possible POIs. So we do a sine graph for the second derivative. So we have to consider -1 and we have to consider 1. So I am going to select 3 different test values for the 3 different intervals. Because again, this tells you what's happening from negative infinity to -1. This tells you what's happening from -1 to +1. And from 1 to infinity. So if we substitute, I'm going to call that -2, I guess. So that means we have 2 minus 2 times -2 squared over -2 squared plus 1 squared. A lot of negatives flying around there. So in the numerator, we have 2 minus, that's 2 times 4, which is 8. 2 minus 8 is -6. And yeah, I have something squared in the denominator, so I kind of know, but that's just going to be 25. So that's less than 0, which means we're concave down. So you can probably guess how the rest of this is going to go. Usually they alternate, but it never hurts to check. Plug in 0. Now 2 minus 0 is 2. 0 plus 1 is 1. Squared is 1. We get 2. So that means we have positive concavity or concave up. And you can probably predict what's going to happen at 2. But again, we'll just write this out so we have the complete picture. Lots of 2's in this problem. And that should again be -6 over 25, which means concave down. So we definitely have a lot of information here. Now we're concave up on the interval -1 to 1. And we're concave down on 2 intervals, negative infinity to -1, and also 1 to infinity. And remember, when 2 different intervals make up the answer to the same question, we put a union in there to show that all of those numbers satisfy that condition. And we have points of inflection at x equals 1 and x equals -1. So to summarize all of this, remember that the original function was natural log of x squared plus 1. So at -1, we have a point of inflection. And if I plug in -1 for x, well, I get the natural log of -1 squared plus 1, which is the natural log of 2. And we'll leave that in exact form for now. We can approximate that later if the problem requires us to do so. When x equals 0, this was my minimum. We get the natural log of 0 squared plus 1, which is the natural log of 1, which you might remember is 0. And once again, at 1, we have another point of inflection. So again, we have natural log of 2 as the y value. Now if I go back up to the graph, that actually looks about right. So if I update my point of inflection here, I'll just make it bigger to make it look like it belongs there. It looks like the y-coordinate is just below 1, and the natural log of 2 is about 0.7. So that verifies all of our results here. So that's finding mins and maxes and whatnot for a transcendental function, not a polynomial. Hopefully you found this video helpful, and I thank you for watching.